Hello everyone. Today we have a rotational dynamics question. A mass of 1 kilogram that's free falling, causing a pulley of radius 0.1 meters to rotate clockwise. And we want to find the angular acceleration given that the moment of inertia of the pulley is 0.0428 kilograms meters squared. So we're going to consider two things: the linear motion of the mass just falling, and then we're going to consider the rotational motion of the pulley turning clockwise. And we're going to apply Newton's second law, F equals ma, and torque equals I alpha for the rotation. So let's start with F equals ma for the linear motion, and taking the downwards direction as the positive y direction. The weight is going to act downwards, W is equal to mg, in the positive y direction, and the tension is going to act upwards in the negative y direction. So substituting that in here, we're going to get mg minus t is equal to ma, and we're just going to rearrange and solve for t. So taking that over here, this over here, t is equal to mg minus ma. Okay, now we're going to do the same thing, but for the rotational motion. So the equivalent to Newton's second law, as I said, would be the torque tau is equal to moment of inertia I times the angular acceleration alpha. So the torque is going to be given by the tension, which is causing it to be pulled in a clockwise rotation, acting downwards, acting at a distance of r from the axis of rotation. So we have this force T acting perpendicularly to the axis of rotation at a distance r. So the torque is given by r cross F in general, which is equal to I alpha. And in this case, since these are at a 90-degree angle, that just becomes r times t is equal to I alpha. So we have an expression here for t. I'm going to substitute that into this equation. So let's just make sure this is clear here. Okay. So we're going to do r times mg minus ma is equal to I alpha. And we want to solve for alpha. So there is a relationship between the angular acceleration alpha and the linear acceleration a. And that's just a is equal to r alpha. Okay, cool. So now we're going to substitute that in. So we have mg r minus m r squared alpha is equal to I alpha. We're going to collect all the terms involving alpha to solve. So we have mgr is equal to alpha brackets I plus mr squared. And solving, alpha is equal to mgr over I plus mr squared. Substituting in our values, that's just 1 kilogram times 9.81 times the radius 0.1 over 0.0428 plus the mass 1 times 0.1 squared. And that's going to come out to 18.57, which is about equal to 18.6 radians per second. So, when I first approached this problem, I thought it was a little weird how the tension in one instance acts upwards, but then on the pulley it's causing it to act downwards. But if you think about it, this makes sense. It's like in a tug of war where, the people pulling from the right-hand side and the left-hand side, the tension must act in opposite directions. So a similar thing going on here. And we can also use our right-hand rules to verify that this expression does actually make sense. So using the right-hand rule for vectors, we can use the rotation. So the rotation is given by the curl of my fingers, right? So it's rotating clockwise like this, okay? And that would mean that the torque is pointing into the page. Right? You see that? It's rotating like that, so torque is pointing into the page. Okay, now we're going to consider R cross F vectors. So the R, using this right-hand rule, is going to be acting sort of this way. And then the T is going to be acting downward. So this is R, this is T. And so we can see that the torque does indeed go into the page. Right, so that might be a little counterintuitive because the angular acceleration, you might think, oh, okay, the angular acceleration is in this direction, it's just alpha. But in reality, when we think of the vectors, the clockwise rotation means that the torque points into the page. Therefore, the angular acceleration also points into the page. And we can verify that the tension must indeed be downwards here, even though it's upwards in the linear equation. Because when we take the R and we cross it with the T pointing down, so R pointing this way, T pointing down, our thumb does point into the page. So that's just a quick aside on maybe helping you understand exactly how these vectors work when we think about rotation. It can be quite counterintuitive, and then why in the linear case the tension acts upwards. When we consider the rotational motion, the tension acts downwards. And if you think about it, that must make sense because how can this pulley be pulled clockwise unless there's a tension here pointing downwards?